video, I want to talk about direct or linear impact. Now, impact is a natural occurrence, and I alluded to a couple of examples in my momentum video, talking about how when two things come together and they make contact and bounce off, that's a useful scenario to analyze the situation using a momentum basis, due to the short time frame over which that impact between those two things occurs. So we need to start thinking about, well, what does it mean to interpret an impact? And when I talk about impact, I'm talking about two objects, and they each have their own velocities, and they're moving towards each other. And these two objects that I've drawn here are moving along, if I could draw accurately, moving along a line until they make contact. And this line we're going to refer to as the line of impact, appropriately enough. So as these two things come together, make contact, then bounce off each other and return in the opposite direction, there's a few different things going on, all in a very short time step. So we start with these two, let's just go with balls, we're going to call them two balls, coming together with some velocity. Let's call that velocity VA1 and VB1. Now, the subscripts A and B are to indicate the two different balls, and the subscript 1 is to indicate that this is the initial state, the initial velocity before they make contact. So they're moving towards each other, and then they make contact. And if the balls are sufficiently squishy, we would see the deformation pretty obviously, but even if they're relatively hard, there's going to be some minuscule amount of deformation, and we may just not be able to see that. So during this case, or this portion, we're seeing deformation of those two balls once they've made impact. Then they're going to begin to ricochet off each other and release. And if we looked at a snapshot just before they separate, they would just be sitting right next to each other. And we're going to call this restitution. And basically this is a snapshot again that right after that deformation has occurred, released, and now the two balls are just sitting next to each other in the process of moving away from each other. And finally, the two balls are now moving away from each other, and we're going to label this velocity VA2 and this velocity VB2. Great. So we've got kind of the picture of what's going on as these two objects are coming into a collision and colliding. So now we're going to take something we've already talked about, which is the conservation of momentum. And I'm going to write out the equation that I think would describe this scenario. So we have momentum of the first momentum of the second, and that has to be equal to the momentum of the first after collision and the momentum of the second after the collision. Now, we didn't include any sort of impulse term in here because we don't have any external forces involved. There's no additional forces being applied to our objects, so therefore that term is zero. Now, if we think about, say an average situation, two balls coming together, making collision, let's say billiard balls, and we are likely to know or to be able to measure the masses of each, and those masses haven't changed from before to after the collision. We can probably say we might know the velocity of each beforehand because we've pushed them towards each other or shot them towards each other with some known or measurable velocity. And perhaps it is the velocities after collision that we don't know that we're trying to figure out. Now, the problem that we should see right away when we look at this is that we have one equation, but we have two unknowns, the velocity of A and the velocity of B, right after the collision. So that's a problem, right? We don't have enough information to solve this problem at the moment. So to start to think of this, we need to think about, well, what could we do to alleviate that problem and come up with more information? And one thing that we can think about is what is happening during this impact. So if I zoom in on just one of the balls during impact or upon impact, treat it like a free body diagram. I'm applying a force. We're going to label it F1 for kind of consistency with our situation. And that force causes or leads to a deformation of the ball. So some sort of flattening or indenting of that ball when it makes that contact. And again, if it's a stiff ball like a billiard ball, that deformation is going to be small, but it's still there. So we apply a force, we get a deformation. What happens next? The ball undergoes restitution, where the two balls are pushing each other apart such that they will fly away from each other in the opposite direction. So in that condition, again, if I zoom in on one of the balls and treat it as a free body diagram, this ball is now applying a force outward on the other ball and pushing it away. And as a result of that force, it is regaining its original shape. So it's returning to its original round shape. And that's the restitution portion of it. So now that we've defined these two things, F1 and F2, well, one thing we could observe is that in general, F2 is going to be less than F1. And the reason for that is inefficiency, which we talked about in a prior video. So when this collision happens, there's potentially some sound, some vibration, maybe a tiny little bit of heat, things like that get lost, right? So that inefficiency means that energy is lost, means that force isn't going to be recovered in the same way or in the same value or amount that it was put in. So to deal with this, we're going to introduce another quantity, the coefficient of restitution. And we're going to use a lowercase letter e to denote that. And the coefficient of restitution is basically a measure of how much energy is lost. I mean, it's basically, you can think of it as an efficiency. And this coefficient of restitution we can write out as F2 times delta T over F1 delta T. So it's basically this force over the time over which this is all occurring. And we can then equivalently write this in a form making use of the velocities. So again, really what we're doing is we're measuring the relative loss of energy with some terms being crossed out and such if we were to go through the derivation of this. The relative loss of energy between the before the impact and the after the impact time states. So this equation that we've got here now gives us another equation on the basis of the velocities that we could make use of. Now, of course, for this to work, we need to know the coefficient of restitution, right? And the coefficient of restitution is itself a material property. we could actually measure the coefficient of restitution. There would be a pretty common or easy experiment to do it with, and that is, or to calculate it, and that is that if we took a ball and we dropped it from some height, let's call it h1, onto a surface, and then we measured the height. I'm going to change my arrow here to be one directional. We measured the height that the ball returns to after that bounce. We can take that and use it to solve for the coefficient of restitution, assuming that the materials are the same as whatever it is we're trying to analyze for our billiard ball example, or maybe a baseball example. So it's primarily a material property. It's similar, to a friction coefficient in that it's an interaction between materials and how much deformation we can expect and how much energy we can expect to regain out of that system after the deformation has occurred. All right, thank you.